In this talk, I will describe an optimal logarithmic time data structure for the dynamic point location problem. In the point location problem in 2 dimensions, we're given a set of n non-intersecting segments, which divide the plane into subdivision. And when we're given a query point Q, like this one, we want to identify the polygon that contains the query point Q. So in this example, it will be this red polygon. So the point location problem is one of the most fundamental problems in computational geometry. It has numerous applications, for example, in geographic information systems, computer-aided design, and other areas. In the dynamic version of this problem, we're allowed to remove or delete some segments. So here, these 2 red dashed segments are deleted, and we can also insert new segments. So suppose that we also insert these 3 blue segments. And now when we ask the same query point Q, the answer will be this red rectangle, or this red triangle. So the 2D point location problem can be actually viewed as a generalization of one-dimensional predecessor search. Example of the predecessor problem is shown here below in the slide. So in this problem, we store a set of one-dimensional points. And when we're given a query point Q, we look for the largest point smaller or equal to Q, like this red one would be, for example, the answer to this query Q. If our point coordinates are reals, then the problem has logarithmic bound on both queries, and logarithmic lower bound on both queries and updates. So the best we can hope to achieve is logarithmic time for queries and logarithmic time for updates. So in the static scenario, this problem was solved completely in 1986 by Sarnak and Tarjan, who described the first linear space data structure with log n query time. But the dynamic point location problem appears to be significantly more challenging. In fact, the existence of dynamic point location data structure with logarithmic query time and logarithmic update time and linear space usage has been asked as an open question at least since early 90s. So probably for the first time, it was asked in the survey by Chazelle in 1991, then in the other survey in 1994, and then also in several other surveys on computational geometry and dynamic data structures. So here on this slide, you can see the most significant previous result on this problem. So you can see that this problem is actually very difficult. The progress was relatively slow, with 1 or 2 results published every 10 years. And so in this paper that I present here, we finally achieve a linear space and log n time for queries, log n time for insertions, and log n time for deletions. In this table, what is not included are many other results that deal with special cases of the dynamic point location. So now, when we solve the dynamic point location problem in its most general form, we usually do it by solving another problem, which is called vertical array shooting. So in the vertical array shooting problem, we're just given a set of n non-intersecting segments, like here. They do not necessarily constitute a subdivision of the plane. And now when we're given a query point Q, we want to report the first segment or the segment immediately below this point Q. Or in other words, suppose that we drop a stone from the point Q or shoot a downward vertical ray from Q, then we must return the first segment that will be hit by this ray or hit by this stone. So if we can solve vertical ray shooting problem in log n time, then it's known how the dynamic point location can be reduced to this problem. So if we can solve vertical ray shooting, we can solve the dynamic point location within the same time bounds. So now the challenge is now to solve the vertical ray shooting problem. The entire solution that was achieved in this paper is relatively technical. It contains many technical details. What I will do in this talk instead is I will give a very high-level presentation of the problem and why it is so challenging, and briefly explain how this challenge was addressed in previous papers and in the paper which I'm presenting here. So the base structure that we use to solve a vertical ray shooting problem is called a segment tree. You can imagine it as a binary tree. And we associate a vertical slab with every node, like here. And we keep for every node, we keep a list of segments that have several properties, but it's important that all segments stored in a node will span the vertical slab. And of course, in order to answer queries, these segments must be ordered, like here. So if you look at this picture or this general approach, it's in fact a very, very standard approach to solving geometric problems. So it appears very often that we store a base tree data structure, and then we store some geometric objects in every node, and these objects are ordered. It appears in segment tree, interval trees organized in the same way than range tree. And there are dozens and probably even hundreds of papers that follow this general approach. And the dynamic point location is probably one among the most difficult ones, or among the most challenging ones that use this general scheme. The reason why it is so difficult to solve is because we cannot maintain a global order of segments. So for example, here's just a small example to explain what I mean by maintaining global order. When we maintain an order, it should respect the vertical ray shooting queries. So if I shoot a vertical ray, for example, like from this point or from any other point, then it should hit the larger segment, the segment which is assigned a larger number before it hits a smaller segment. So such an ordering can be easily constructed, as shown here. So we assign the segments or numbers 7, 6, 5, then 4, 3, 2, and 1. However, if I remove this segment S and insert another segment S prime, then now the same vertical ray shooting query will hit S prime, and then it would hit S 3, 2, and 1. And you can imagine that here we have another query that should hit this segment, this, and this segment before it hits the segment S prime. So now, of course, S prime should be assigned number 4, and these 3 segments will be 7, 6, 5, and these 3 segments will be 3, 2, and 1. So you can see that the order of segments has changed in a very significant way, and it was achieved by just deleting and inserting one segment. So even a very small number of insertions and deletions can change the order of segments, the global order of segments, in a very significant way. And this lack of a global order is what makes it difficult to apply some of the standard techniques. And this is what makes the problem itself so difficult. So now, since we have no global order, we must maintain the order. We have to maintain the order of segments in every single slab. But in the segment tree, every segment will be stored in roughly log n nodes, roughly log n times, and we'll have to visit about logarithmic number of nodes in order to answer the query. So now suppose that I insert the segment into this node, this black segment, into the slab associated to this node, what will happen is I will need to do a binary search among segments in this slab. It will take logarithmic time. Then I will move to this node, and again we'll have to do logarithmic search, binary search here to find the proper position of this black segment, of this bold segment. So since the number of nodes which I have to visit in such way is logarithmic, the total query time will be log squared n. And the same for updates. So every insertion will take will have to visit log n nodes, and then every node will have to answer, or will have to find the proper position of the segment, which will take logarithmic time. So the total time will be log squared. For queries, it's the same. We'll have to visit some nodes on the path from a root to a leaf, and then every node will potentially have to do binary search again, and this will result in log squared n query time. So the first improvement to this general scheme was achieved in the papers by Baumgarten in 1994, and then by Arg and others in 2006. So in these papers, the authors have shown how we can use a technique called fractional cascading in order to improve the query time, and they have finally achieved even log n time for queries. However, the update time still remains very high. It's roughly log squared n, at least for one of the two update operations. And this is clear because we'll have to do binary search log n times when we do updates. The next improvement to this scheme was achieved in the paper by Chan and Nekrich in 2015. And the main idea of their paper is to assign different categories or different colors to segments. And this can be done in such way. So here you see there's some green segments, red and blue segments. And this can be done in such way that segments of the same color, like red segments here, are ordered even if they're stored in different nodes. So we cannot maintain the order of all segments, but we can maintain the order of segments of the same color, even if they're stored in entirely different nodes. However, there is one drawback associated to this approach. We do not know the global order of all segments in this lab. We just know the order of segments of the same color. And this means that when I answer a query, like here, I'll have to answer it separately for each color in this lab. So first, if I have a slab like this one and a query like this one, I'll first answer the query for green segments, then I'll answer the same query for red segments, and then the same query for blue segments. So the number of the query time will grow by the number of colors associated to every slab. So this enables us to achieve different trade-offs for queries and updates. Probably the best one is log times log n query time, and log times log n update time. Or one can achieve log to 1 plus epsilon query time. Epsilon is an arbitrarily small constant, and log n update time. Or vice versa, we can achieve optimal query time, log n, but then the update time will grow to log 1 plus epsilon. So those trade-offs are relatively efficient, But unfortunately, the same approach cannot lead us to logarithmic time for updates and queries at the same time. At least it appears to be not possible. And the reason is that if the number of colors associated to every node is constant, then the update time has to be log to 1 plus epsilon. And vice versa. So if we want to achieve log n query time, log n update time as here, then the number of colors associated to each node will be log to epsilon n. And the query time will have to grow by this factor, and it will be like this. So in order to achieve optimal time, we're going to use some additional ideas. And so this is what we achieve in this paper finally. It's logarithmic time for queries, logarithmic time for updates, and linear space. And the main idea is probably the fact that we don't have to maintain the order of all segments in each slab. So our idea, just at a very high level, our idea is as follows. We select some nodes. In fact, we select all nodes on every log to the delta n level of the tree. And delta is some constant which is larger than epsilon. So we roughly divide the tree and look at every log to the delta nth level and select all nodes on these levels. And we store some additional or auxiliary lists of segments, which will be colored. And in all other trees, we'll store lists of segments as in a segment tree, but those lists are going to be incomplete. So here are some details. This is how this auxiliary list looks like. There will be, in fact, log to the epsilon n different colors. But in this auxiliary list, which is shown here, we only know the order of segments of the same color. So, for example, I know that for this blue segment, this will be the preceding blue segment, and for this red segment, this will be the preceding red segment. But I don't know the relative order, for example, of red and blue segments, or red and purple segments. So the total order of segments in this auxiliary list is not known. And still, this list can be helpful for us. What we do, we divide it into groups of roughly log squared n segments. And for the first segment in each group, we know its position in the total order of segments. So this means I can find for this segments shown here in squares, what will be the preceding segment of any color. And I can do it quickly. So now consider insertion of a new segment S. I have to remember that I don't have to insert them just into selected nodes. I have to insert them into all nodes. Like, for example, first into this one, then into this one, and so on. So now, so I'm inserting this into this slab. And there are two situations. First, I will find the segment, which is called a reference segment. It's called your SP of U, like this one. I will not define what it is, but this SP of U can be found quickly. And then I'll try to insert the segment S above SP of U, but in the neighborhood of SP of U of polylogarithmic size. So if S should be stored somewhere close to SP of U in polylog neighborhood, then the segment S is going to be, I will find the proper position of S and insert it into the list of segments for this slab. Well, but there's, and this can be done in log n time. But there's another situation when this is SP of U, and there's a huge number of segments between S and SP of U. Well, in this case, I'm not going to insert S into this slab at all. I will say that S is an implicit segment, it will not be stored at all in the list of segments for this node. So that's what I meant when I said that the list of segments is incomplete. Now, there is of course a problem, because when I answer a query in this slab, like, okay, this is the same slab, and I answer a query Q for this point Q, this segment S, which is an implicit segment, will be just missed. So implicit segment will of course be missed. But it turns out that if I miss the segment S, then I found of course my query found some other segment S prime where it stopped, where this vertical array shooting, where this vertical array has stopped and hit the segment. And this other segment S prime is going to be close to S in some sense. And this means that when I visit this segment, the ancestor, the selected ancestor of the segment of this node U, then I will be able to quickly find this segment S if I know S prime. So this is what will actually happen in this segment. In the selected ancestor, so this is the segment S, which was missed. Probably there's another segment which was missed. And then there's a segment S prime, which was found by the query so far, which was found when we answered queries in descendants of this select node. So I don't even know the color of the segment S in this auxiliary list. But I know what I can quickly do is to find the group where S can be stored potentially. So if there is a segment S that was missed by the query, then I can find the group in which this segment S can be stored, or can be stored. And there's just one such group. So what will happen if I know S prime, I will find for every color the group where S can potentially be stored, and then search in this group. So in this case, I will find this group, the first segment of this group, and then search here in log n time, and then I will find this segment S before Q, and this will just take log n time. But of course, I have to do it for all colors. Therefore, there will be log to the epsilon n colors, and the total time is log to the epsilon n times log n, which is big O of log to the delta. And if I sum it over all selected nodes, the time is just big O of log n. So this is just a very high level idea. And of course, once again, the idea is that I don't have to store total order for all segments. There are many other details which I didn't describe here. You can find them in the paper. For example, there's one special case of middle segments where a different approach is used. We use special segment labeling to speed up updates. And also the tree is not a binary tree as I have shown before, but actually we need to use a tree with no degree, log to the epsilon n, so that the height of the tree is log over log n. So if we combine all these ideas, then as I said, we will be able to achieve logarithmic query time, logarithmic update time, and linear space usage. And this solves the two-dimensional dynamic point location problem. Thank you for your attention, and thank you for listening to this talk.